So welcome you back to this module. So in last module we discussed some of the properties of the roots of the likelihood equation Lx prime theta is equal to 0. So the first important result which we did in this direction was that they will, so under certain conditions which are very non-trivial trivial kind of conditions, that there should not be any identifiability issue. That means my probability distributions under consideration should be identifiable. Parameter space theta should be an open set. And the support of the distribution should not depend on theta. So that means uniform 0 theta kind of densities are not covered. So under these three conditions, there will always exist a sequence theta and hat star x of estimators such that probability that theta and hat star x is a solution of the equation Lx prime theta is equal to 0, this would always go to 1 as n goes to infinity. Not only that, probability that theta and hat star x is a local maximum of Lx theta, that probability would also go to 1 as n goes to infinity. Not only that, this theta and star x will always be consistent. So there will always be a sequence of consistent estimator for theta, which in many cases the best possible candidates or the possible contenders for that would be the roots of the likelihood equation Lx prime theta is equal to 0. As a consequence of this result, we concluded that if your likelihood equation Lx prime theta is equal to 0 has a unique root, then such sequence of solutions would be consistent. Then we further said that any consistent solution of Lx prime theta is equal to 0 would have an asymptotic normal distribution with mean as 0 and variance as 1 upon I theta naught. So if we combine all these results, what we get is, if my likelihood equation is such that it has a unique root, and such a unique root is consistent, then the estimator, such a sequence would be asymptotically normal, or it would be can and most efficient, asymptotically efficient. In addition, if these equations, these solutions which we get are also the local maximas, then they would be the MLE. So in those situations, this result proves the consistent and asymptotic normality of maximum likelihood estimators. Not only that, they also show that maximum likelihood estimators are asymptotically efficient. Then we saw the exponential family and said that in exponential family, all those conditions under which these results were holding are satisfied. So let's go further for the exponential family. So theorem for the one parameter exponential family, which we wrote last time. What was that? F theta x, which is same as e to power theta tx minus psi theta into hx with respect to sigma finite less than where theta belongs to the natural parameter space, which is nothing but collection of all those eta belonging to R, says that e to power integral over e to power eta dx hx d mu is finite. And I assume that theta is an open set. If theta is not an open set, I consider theta to be its interior. Then the equation Lx prime theta is equal to 0 has a unique solution theta and hat star x for every n and x. So you can write down small x for every small n and x, such that this theta n hat star x is the MLE of theta. Now once it is MLE of theta, it has a unique root, so it is consistent. So you know that root n theta n at x hat star x minus theta naught would go in distribution to normal 0. 1 upon I theta naught. Just follows from the last result, because as I have been saying, if your likelihood equation Lx prime theta is equal to 0 has a unique root, then such a root would be consistent. Now if it is consistent, by last result it would have asymptotic normality. Now if it is also MLE, then you can say that MLE is consistent and asymptotically normal. So the proof, if you look at what is Lx theta, which will be product I is equal to 1 to n e to power theta txi minus psi theta, sorry, into hxi. Theta belongs to theta. So Lx theta, which is log of Lx theta, is nothing but theta times. What I'm assuming is here psi double prime theta is greater than or equal to 0. Assume psi double prime theta is greater than 0 for every theta belonging to theta. So that is a part of assumption. So Lx theta is same as log of Lx theta. So summation I is equal to 1 to n, so that becomes theta summation I is equal to 1 to n txi minus n psi theta plus summation I is equal to 1 to n log of h of xi. So I consider the partial derivative with respect to, this is what I have to maximize to get the maximum likelihood estimator, which is nothing but summation I is equal to 1 to n txi minus n times psi prime theta. Now this is greater than 0 or less than 0, depending on where psi prime theta is less than or greater than 1 upon n Note that psi double prime theta is strictly increasing, because you are given that psi double prime theta is strictly positive for every theta. So that means psi prime theta is increasing. So that means inverse always exists. So this is equivalent to saying that theta is less than or greater than psi prime. If it is strictly increasing or decreasing, so inverse always exists of 1 upon n summation I is equal to 1 to n t of xi. And this is nothing but theta n hat star x. So what do you get? Your function is strictly increasing first and then strictly decreasing. So this is what your Lx theta is. And this is theta. Up to theta n hat star x, it is strictly increasing because psi prime theta is strictly increasing. And then it is strictly decreasing. So theta n hat star x, which is the unique solution, is the unique solution of now the result follows from the last theorem. So use last theorem to get is the solution of this thing, and it maximizes Lx theta. So in other sense, it is the MLE. If it is MLE by the last result, it is consistent and asymptotic normal because it is a unique solution of Lx prime theta is equal to 0. So, so the discussion which we did so far suggests that maximum likelihood estimators in many situations, especially in the exponential family, would normally be consistent, asymptotically normal, and asymptotically efficient. Now, this theory of maximum likelihood estimator can be used to find sometimes asymptotic confidence intervals. Let us try to see how do we do that. So what I'm trying to do is I'm trying to see some applications of the results which we studied so far, which were basically in context of proving that maximum likelihood estimator is consistent and asymptotic normal. Now, if you have asymptotic normality, your maximum likelihood estimator sometimes may not even be in a closed form. It may be a solution of certain complicated equation. But last theorem suggests that in certain situations, this maximum likelihood estimator would have an asymptotic distribution, which is normal. So the nice properties of normal distribution can be used to get asymptotic confidence intervals for the desired parameter theta based on the MLE. And that is why these maximum likelihood estimators are considered to be very important and very nice estimators, because they have a very nice asymptotic properties. So let us try to see some result. So asymptotic confidence intervals, CIs. First, I do it using MLE. How do you use MLE? So under certain conditions, so we can write down regularity conditions, which are certainly satisfied in the case of one parameter exponential family. And these are the conditions which we stated in that theorem. We talk about that your log likelihood function is differentiable, its third derivative is bounded by a function which is integrable, and so on. So under certain regularity conditions, suppose that theta and hat x is the unique MLE. Then you know that root n theta and hat x minus theta goes in distribution to normal 0, 1 upon I theta naught. So for a given alpha belonging to 0, 1, I can use the percentage points of normal 0, 1. So that means this divided by I theta naught would be normal 0, 1. So that means probability limit n going to infinity. Probability under theta naught that minus z alpha by 2 is less than or equal to root n theta n hat x minus theta naught by square root of I theta naught is less than z alpha by 2 is 1 minus alpha. Where what is z alpha by 2? Z alpha by 2 is this point. So that on the right of normal 0, 1 you have a alpha by 2 region. On the left of it, on the left of minus, so by symmetry on the left of minus z alpha by 2 would be alpha by 2 region. These are normal 0, 1 PDF. So that means z alpha 2 point is such that phi of z alpha by 2 is nothing but 1 minus alpha by 2. On the left of phi z alpha by 2, there is a 1 minus alpha by 2 regions. So what does that mean? This implies that, so I can solve this. So minus z alpha by 2 less than or equal to root n theta n hat x minus theta naught. So this is a certain inequality. I can solve this inequality in terms of a theta naught to get a 101 minus alpha % confidence interval for, can be solved, thus can be solved to get a 101 minus alpha % confidence interval for theta naught. So solving this sometimes may be easier, sometimes because it's an inequality. And this I theta naught may be a non-linear function. Then sometimes solving this inequality may not be that easy. Of course, in exponential case, you know that this I theta naught is nothing but psi double prime theta naught. So if psi double prime theta naught has a nice function, you can solve it. Now in situations where this doesn't has a nice function, I should try to get an estimate of I theta naught. If I can get a consistent estimate of I theta naught, and if I replace that over here, I get some convergence in distribution. So let us try to see what is I theta naught. I theta naught, if you see, is nothing but E theta naught of del by del theta naught square of log of f theta naught. So it is the mean of this thing. So I can use the strong law of large numbers. I can use corresponding sample means of IID observations, and that would converge to over here. So that means I considered 1 upon, so I minus I theta naught is this. So summation I is equal to 1 to n del square by del theta naught square log of f theta naught xi will go almost surely to, so you can put it here, minus to I theta naught. And you know that theta hat star converges in priority to theta naught because it is consistent in MLE. So what you know is I theta n hat star converges in priority to I theta naught. So if you want, you can get this estimate or this estimate if you want to use the MLE. So you can replace here by root of I theta naught. So that means what you get is root n theta n hat x minus theta naught by square root of I theta n hat star. There is no theta n hat is the MLE I'm using. Theta n hat is the. This again will go in distribution too because this goes by Stratsky's lemma, this goes in priority to I theta naught. So everything would go to normal 0, 1. So again, the same confidence interval can be used with I theta naught being replaced by I theta n hat star. So this implies that 101 minus alpha percent confidence interval for theta naught is. So I replace here by I theta n hat star because that is a consistent estimator. And one can use this estimator also, but theta n hat is a nice estimator. So I would prefer this estimator unless it gives a complicated expression or poses some other kind of problems. So what do you get? So if you do that, then you get theta naught. This is this thing. So theta n hat x minus z alpha by 2 root I theta n hat by root n 2 theta n hat x plus z alpha by 2 root I. So this is the 101 minus alpha percent confidence interval for theta naught. So you see, using MLE, you can get a nice form. One could have used this also as an estimate of I theta naught. So one can get different kind of confidence interval. So there is another approach to find asymptotic confidence intervals, which is using score function. So let me write down. Let me explain that procedure. Of course, using the method based on MLE is always good because, as you know, the MLE would be a function of a sufficient statistic whenever it exists. In fact, it would be a function of a minimal sufficient statistic. So using score function. So let us write this function as x theta, which is del by del theta of the joint density g theta x. So all these which we are holding are holding only for one parameter families. So this I write down as summation I is equal to 1 to n del by del theta log f theta xi. So this g theta x, I think I was denoting joint density. So let me directly denote s x theta as this, which is del by del theta of joint density of theta. So this is actually same as del by del theta of log of g theta x. This is joint density, and that is same as this, which is same as summation I is equal to 1 to n si. Let me call this function as score function. What is the expected value of S1? So this is, these SIs are IID because XIs are IID. Let us try to see what is expected value of S1. It would be f theta prime x1 upon f theta x1, which we have seen is 0. What is the variance of S1? That is the variance of del by del theta of log of f theta x1, which is I theta naught. So by central limit theorem, root n s bar minus 0 by square root of I theta naught goes in distribution to normal 0, 1. So what you can say is p theta naught minus z alpha by 2 is less than or equal to root n s bar I theta naught is less than or equal to z alpha by 2 is equal to 1 minus. So if you want, one can get this. You might want to use an estimate of I theta naught. One such estimate could be I theta and hat star. And one can get confidence intervals by inverting these statements, and if required, using an estimate of I theta naught. So let me finally do one example quickly. x1, x2, xn are IID, normal 0 theta. Theta is positive. What is the unique MLE? You know from your last course, theta n hat star x is 1 upon n summation I is equal to 1 to n xi square is the unique MLE. What is I theta over here? You have already seen normal 0 theta. It is the variance inverse, so 1 upon 2 theta square. So which is basically a minus expected value of del square by del theta square log f theta x1, which is how much? Some constant 1 by theta to the power minus half would come, so minus half log theta, right? Because 1 upon root theta, 1 by sigma, 1 by root theta, root 2 pi, that gets so minus 1 by twice theta summation xi square, right? That is what the thing would come. Sorry, only there is only one observation, minus x square by 2 theta. x1 square by 2 theta, you can write it down. This is expected value of second derivative of this. So del square by del theta square when you look at the first derivative, it becomes minus 1 by 2 theta plus 1 by 2 theta square expected value of x1 square. And then derivative of this. Derivative of this becomes minus times expected value of 1 by 2 theta square plus 2 upon theta to the power minus 2 minus 2 upon theta cube. You can just put x1 square. x1 square is same as theta, so it becomes 2 by theta square minus 1 by 2 theta square, so 1 by 2 theta square. Right? So what you get is, root n theta n hat star minus theta naught divided by square root of I theta naught, which is same as 1 by root 2 theta naught, probability that theta naught minus z alpha by 2 less than or equal to z alpha by 2. So if you want, you can get an estimate. So one thing is you can replace here theta naught by square root of theta naught hat, because theta hat star goes to theta hat. So you can say that probability of theta naught limit minus z alpha by 2 root n theta n hat star minus theta naught by 1 upon 1 by root 2 theta n hat star less than or equal to z alpha by 2 is 1 minus alpha. So I have just replaced this theta naught by its consistent estimator, and in this case you know that MLE is a consistent estimator. So you can get a confidence interval for theta naught. Of course, one can use the score function as well over here. So try to use the score function and get a confidence interval. So let me stop for this module over here. In the next module, we'll start with a new topic, which would be basically testing of hypotheses. So in testing of hypotheses also we had a similar problem, that if we consider all tests into consideration, the best test does not exist because your power function depends on theta. So we try to pose certain restrictions over there. So in the last course, one such condition was that your test should be unbiased. That means power should always be bigger than or equal to size of the test. And among all such tests, you try to find out the best test. Another reasonable criteria could be that you only consider those tests which are invariant. So what we'll do in the next couple of lectures is we'll restrict to wherever the testing problem has a nice structure. I'll try to restrict only to those test procedures which have a nice structure, which would be basically in our case the invariant tests. And then among invariant tests, I try to find out the best tests. So that's all for today. Thank you very much.